Welcome to another episode of Progress, Potential, and Possibilities, discussions with fascinating people designing a better tomorrow for all of us. I'm your host, Ira Pastor.
Welcome, everybody, again to another episode of our show, bringing you another really great guest today involved in creating a better tomorrow, really doing some very unique science. We have the honor today of being joined by Dr. Heather Whitley, who is Associate Program Director for High Energy Density Science, part of the Weapons and Complex Integration Directorate at the Lawrence Livermore National Laboratory, where she is responsible for providing technical oversight and management of the design, execution, and analysis of area experiments done at the National Ignition Facility, which we profiled last week, but also other laser programs that they have. Prior to this particular role, Dr. Whitley also served as a detailee on assignment to the National Nuclear Security Administration Defense Programs Office of Experimental Sciences. Dr. Whitley completed her graduate studies of quantum systems at University of California, Berkeley, with a Ph.D. in theoretical chemistry prior to joining Lawrence Livermore as a postdoc researcher back in 2007. She was hired as permanent staff member in 2010 and was recipient of the 2011 Presidential Early Career Award in Science and Engineering. And her work at Lawrence Livermore has broadly supported the physics, data, and modeling needs of both nuclear warhead studies as well as high energy density experiments. She was awarded the NNSA Defense Programs Award of Excellence twice in 2018. Aside from all that, she's also a very accomplished ballerina and ballet instructor. And in addition to her work in quantum systems and theoretical chemistry, she attended New Mexico State University, where she did undergrad work both in chemistry and French, and also minored in physics. A lot of really interesting topics to get into today. Dr. Heather Whitley, thank you so much for taking the time to come on our show today.
It's a pleasure. Thank you.
It's great having you, Heather. I would love to start off by handing you the floor a little bit, just to talk a little more about sort of the beginning of this amazing journey you've been on. Just a little bit about your background, where you grew up, and sort of how some of these initial interests, obviously both in chemistry and physics, led to sort of the next step of your journey in a really wanting to explore what I'll call the bleeding edge of both chemistry and physics.
Sure. So thank you. I would say that I think where I'm at today has exceeded any expectations I had by leaps and bounds. I grew up in Roswell, New Mexico. I'm the oldest of 7 kids. And I was encouraged from a pretty early age, like about 8th grade, I started, excelling in math. And I had a teacher who encouraged me to participate in some math competitions. So that was when I started getting some mail from colleges. And I remember in specific getting a letter from the astronomy department at New Mexico State. Astronomy was actually the one type of science that I was interested in as a little kid. I kind of didn't like science class very much up until high school. And it was in 9th grade when we started applying math to science more in my physical chemistry class at Roswell High School. Physical science class at Roswell High, that I really started to get more into science. And then ultimately, chemistry was my favorite class in high school. So that was part of the reason why I decided I wanted to study chemistry at New Mexico State. I was fortunate to work the entire time I was in college in the chemistry department. The first year I just worked in the chemistry stockroom, but then I got a job actually doing research for 3 years as an undergraduate with Dr. David Smith at NMSU. And that was an incredibly rewarding experience. And that was actually where I got into computation. So my background right now is actually our precursor system to our new El Capitan supercomputer that is currently being developed and built here on site. In Dr. Smith's group, I fell in love with the computers. I was the system administrator, and I started writing computer code to simulate essentially hydration in clays as an undergrad. In my physics minor, I focused on quantum mechanics. And so that was how I got really interested in quantum. And so I went to grad school. Sorry, just a second. I went to grad school at UC Berkeley, and I decided there I wanted to kind of expand, the theoretical methods that I had applied as an undergraduate, get into more quantum mechanical systems. So did my PhD with Dr. Birgitta Whitley at UC Berkeley. She's actually pretty well known right now in the field of quantum computing because she's one of the pioneers in that field. My research topic was not directly quantum computing. It was actually superfluid helium and its impact on molecular spectra. So all of that sort of led me to this point where at the end of grad school, I was like part computer scientist, part physicist, part chemist. And I felt like I needed to focus in to figure out like what I was going to be when I grew up. And that was part of what brought me to Livermore. I came here to do a postdoc in a group that was very focused on electronic structure, which is sort of more core to theoretical chemistry. So I came here to do that. I did do research in theoretical chemistry, but ultimately I started getting drawn into plasma physics, in part just due to like chance interactions. And one of my mentors, Dr. Frank Graziani, was really the person who kind of brought me over into plasma physics. And the same quantum mechanical methods that apply in theoretical chemistry can be applied to plasmas and warm dense matter. So I worked a lot in that field, and as we developed a lot of models, we wanted to test them. And the really exciting thing about the NIF, which starting in 2007, the NIF came online in 2009. It became available pretty early on in my career here. And the really exciting thing about the NIF was that it really gave us the access to some of these very high energy density states in the laboratory for the first time. So I got into designing experiments for the National Ignition Facility and really working with our experimental teams to try to validate a lot of the work that we had done, sort of looking at the theory of plasmas.
Excellent. Really excellent. Yeah, and I know, Heather, as I was sort of looking at your extensive publication history in all these domains that you were just mentioning, the one thing that struck me is sort of not just the range of topics, but sort of the range of temperatures as well, right? Because your research starts off, in Kelvin and negative couple hundred degrees, goes to trillions of degrees when you get into the ignition facility and so forth. I want to start off as sort of your PhD, if we could, just for a couple of minutes, because, the title, as you were mentioning, bosonic helium in nanoscale environments, absorption, energetics, and superfluidity. And I did a little research here just to try to get up to the basic speed. I found out that helium-4 is, an extremely abundant isotope of helium. It has all sorts of cool super fluid dynamics when you chill it down to negative 300 or so, and it doesn't have the spin chemistry because it's a boson versus a fermion, and that's about it. But it sounds really cool, and I know you can do a lot of cool quantum things with it, and we'll get into that in a minute. Talk about sort of when bosonic helium landed in your lap. I mean, what was that all about? Take us back to that.
Sure. So that's really interesting. So in my undergrad research, I had part of my project was really taking a code that was a molecular dynamics code, which is a method that solves Newton's equations of motion to move particles around. And it's a fundamental way of looking at materials that was actually developed here at Lawrence Livermore back in the 1950s, which is cool. But I took that code and rewrote it into a Monte Carlo code, which is something that samples positions stochastically And the reason that we did that is because we wanted to more effectively sample phase space for the clay systems that we were looking at. So I really found Monte Carlo fascinating because it's this sort of, random walk, but, eventually it converges and you get like real, real results, real physics results from this method. And so, I mentioned my interest in quantum mechanics. Going to Berkeley, the thing that really excited me about the research that Brigida's group was doing was quantum Monte Carlo. And so I wanted to apply quantum Monte Carlo. And, usually when you go into grad school, you don't know exactly what your research topic is going to be. And you spend maybe a year or two sort of learning about things and finding a cool question. So I think in the first year or so, I was exposed to a whole bunch of different questions about superfluidity in these nano droplets. So
Mhm.
I should talk a little bit about what that means because this is so far
Please.
outside of the field of maybe what most people think about day to day. So you mentioned helium-4 as being a very abundant atom, which it is. If you expand helium through a jet really quickly, it cools down. So this is just ideal gas law, like PV equals nRT. If you rapidly decrease the pressure, the temperature rapidly decreases, and so you can form these little droplets of helium. And so back in the 1990s, there were a bunch of groups that developed methods for actually embedding molecules inside of these little droplets of
Mhm.
helium. And those droplets are at temperatures like 0.3 Kelvin, right? So they're superfluid, very
Mhm.
low temperature superfluid droplets, and it quenches all of any kind of like thermal motion that's in the molecule.
Yep.
And so the molecule then becomes sort of a probe of the superfluid itself. And the kinds of questions that Brigida's group was interested in were like, how does the helium actually lead to the spectral features that we see for the molecules? Because there was evidence that some of the spectral features that were being seen were due to the direct quantum nature of the helium, which it weakly interacts with the molecule. So that was an interesting thing in and of itself. Um, and then the other thing was sort of, superfluidity is a concept that's macro scale sort of thermodynamics of materials. How does this kind of transition over into the world of Bose-Einstein condensates, where we're looking at finite number of
Mhm.
particles that are truly sitting in the same quantum state versus a superfluid, which isn't strictly in a single state? And kind of what is the minimum number of particles that you need to actually form a superfluid, right? Going from sort of something that's more like a Bose-Einstein condensate to something that's more like a superfluid.
Mhm.
So I ended up focusing my research topic on these planar aromatic molecules, which, I mean, the simplest one is benzene. I think a lot of folks know what benzene is. It's a
Yep.
six-member carbon ring, and it's planar. So graphite is the extreme example of a planar aromatic molecule, or graphene. It's just a whole bunch of carbons in a plane. There's a whole series of different molecules like phthalocyanine, different porphyrins, that actually a lot of these are present in the human body and actually help to carry important elements around your body,
Yep.
like a hemoglobin essentially has sort of a porphyrin-like center, where the iron sits, and that's where the oxygen bonds, and that's how it carries blood, or carries oxygen through your blood all over your body. So I was interested in looking at how the helium was actually interacting with those molecules and whether it was superfluid, what was the quantum nature of that helium. So I applied a method called path integral Monte Carlo, essentially to simulate those systems and to form some hypotheses as to why different spectral features were seen. So that was really my undergrad or my graduate research. And I would say, if you listen to all of that, you're probably thinking, well, why the heck does anyone care? It's really about fundamental physics. It's really about understanding fundamentally how we transition from, very small scale quantum behavior to large scale quantum
Right.
behavior. And then, when you understand things like that, that helps you to do things like supercomputing or quantum computing, really understanding the fundamentals. So actually, when I came out of grad school, I kind of wanted to do something that was a little bit more applied. And
Yep.
that was what that was part of what brought me to Lawrence Livermore as well. So my first project had to do with materials that could be used for solar cells, for example. Yep. I was very interested in sort of more today types of applications, although of course quantum computing has kind of taken off in the last few years as well. So that's exciting to see too.
Yeah, and I appreciate and thank you for going into that. And I will later in the show circle back because I wanted to lay that groundwork as we get into sort of some of the future looking stuff in terms of theoretical chemistries and quantum chemistries and so forth. And of course, because if it worked in quantum dots and a lot of these other, again, I'll call them bleeding edge applications, the things that, are sort of on the drawing board and the neat chemistries that we can ultimately produce. So thank you for laying the groundwork for that. With that, I'd like to go forward a bit so we're going to go from very cold now to very hot. As I mentioned in the bio of the show, you have one of your responsibilities is working and providing your knowledge in both physics and chemistry per oversight per some of what is going on at the National Ignition Facility. We had Annie on a couple of days ago talking about her particular work, but she was describing sort of the fusion work. It's not just while there's lasers and unique chemistry and unique geometries involved in this. It's your responsibility to really go into the fine detail of what's going on there. And again, you have papers on, things like boron plasmas and helium-3. And why I'm bringing this up is because I know, as we discuss the future of fusion and the potential fuels beyond tritium and deuterium, we have to study what other possibilities are. You also have some really interesting there was one paper here on the doping of the capsule with krypton and how that can affect what goes on inside the capsule that holds the fuel. Talk a little bit about sort of your responsibilities per high energy density sciences in making these fusion components perfect.
Sure. Okay. So in the context of the ICF program, a lot of that work that we did was to support materials properties models that go into the ICF modeling. So I know Annie talked a little bit in her interview about the equation of state experiments that she had done. I actually participated in that team as one of the theoretical participants who did some of the modeling and helped to actually form new materials models based on the experiments that were done. So with the boron work that you mentioned, we're actually looking to different types of ablators for ICF. So high density carbon is great, and obviously we've achieved ignition with high density carbon. But one of the fundamental issues that we have with it right now is that our implosions are incredibly sensitive to capsule quality. And so it's been posited that if we could move to something like boron carbide, which doesn't have this sort of ordered crystalline structure that the high density carbon has, that we could potentially have a more efficient implosion. So I was sort of asked to look at the equation of state of boron carbide for those experiments. And then we were also interested for some of the other experiments that we're doing. So you mentioned krypton. It was actually argon, I think, that we doped the capsules with, not krypton, because what we were interested in those experiments was understanding the electron-ion coupling in a plasma. So if you drive a very strong shock in an implosion, not in an ICF capsule, but just in a capsule with a gas fill, you can actually heat up the electrons and the ions to different temperatures. So what happens is that the ions couple more strongly to the shock than the electrons do, and so the ions get hotter than the electrons. And it's the collisions between ions and electrons in the plasma that dominate the temperature equilibration, and eventually the two will come together. So about 10 years ago, we were working on a platform to design a direct drive implosion to study that effect, and we used argon as a tracer to try to measure the temperature separation. Now, we had issues with the way that we built those capsules and trying to analyze the data because there were all sorts of inhomogeneities in the way that it's driven at the NIF. The NIF is built for polar indirect drive
Okay.
ignition experiments, and so the lasers come in from the top and the bottom asymmetrically. And the experiment that we were doing there was trying to directly drive a sphere with the laser. So if you imagine trying to directly drive a sphere and you're pushing on the top and the bottom, it's going to have the tendency to just smush. And so that creates all kinds of inhomogeneities in the temperature field and makes it harder to understand the spectra that you measure. So we looked at boron nitride and boron carbon and pure boron actually as alternatives, because since they have a higher tensile strength than the plastic that we were looking at, we had posited that we could make it thinner. And HGC was also an option there. The nice thing about the boron materials, though, is that they also give you the possibility to do radiochemistry. So I also have a more recent paper with the Los Alamos group who's actually doing some of those radiochemistry experiments using it's a boron doped beryllium ablator. And the nice thing about that is that actually gives us a measurement of how the ablator or the outer part of the capsule is mixing into the gas. So that's a very deep physics deep dive into some experiments that I worked on and models that I helped to develop. My job now is actually managing our portfolio of experiments in the high energy density science program. And so we do everything from like materials properties to support the stockpile, like experiments on plutonium, to very basic science and radiation transport experiments that help to support our ICF program and basically understand the physics that we need to understand in order to improve our implosions.
Heather, one thing that Andy mentioned when she was on the show last week was something about another experiment. It was a sort of a ride-along experiment that was happening sometime in December to go along with the fusion work. Can you tell a little bit what's happening there? Because I know you're integrally involved in that as well.
Sure. So actually on December 5th, we had fielded a piece of hardware that we're designing to hold samples so that we can do radiation exposure experiments on different samples. And so by coincidence, on the actual shot that had ignition, we had put that hardware into the chamber, and we had some depleted uranium samples inside of it, and we successfully measured actually a temperature rise in those depleted uranium samples due to the neutrons that were impinging on those samples inside of the hardware. And this is actually really important for our survivability program because we're standing up this hardware so that we can test different materials essentially for our weapons program inside of that hardware. So really cool coincidence. And yes, I think Annie mentioned that she had talked to one of our other nuclear physicists here who was involved in that shot. So yeah, super exciting for us that it all sort of came together on that shot.
Outstanding. No, really outstanding. So you had this period of time that you spent at NNSA, and one of the guests we had on the show a few months ago was Angie Sheffield, who was talking a little bit about her work on artificial intelligence. In particular, your work, in just sort of reading about sort of the responsibility of the directorate. We have, obviously we as a country, we have a certain amount of nuclear stuff sitting there, and thank God we don't use it, but nonetheless, when stuff sits there, whether it's uranium, plutonium, whatever, things happen over time, chemistries, unique things happen. What type of stuff, obviously no national security stuff here, but what types of things do you look at when you, I guess you have to assess, okay, this plutonium's okay, something's going wrong here. What are the types of things you look at with these heavy, because we talk about boron and helium and a lot of light stuff. Now we're talking with the really heavy part of the periodic table. What types of things are you interested in studying there?
So with plutonium in particular, we've been studying the equation of state phase transitions and the strength of the material. And all of those things are components that go into understanding our stockpile, essentially. And, you sort of alluded to our national security mission. The US stopped doing underground testing of nuclear devices back in 1992. And when we did that, Our laboratory and our partners throughout the complex promised the nation that we would be able to ensure the safety, security, and reliability of the nuclear stockpile into the future. And one important part of that is the supercomputers, like the one you see behind me. Another important part of that is our actual experimental program, right? So building off the data that we obtained during the testing era, we basically maintain our computational capabilities in order to investigate our stockpile. And year over year, we do an annual assessment that goes to the president, actually, on the stockpile. The experimental program is a piece of this because as different physics and engineering questions arise, we can exercise our experimental capabilities to obtain new data to help understand the physics and engineering questions that are relevant to that mission. So there's a whole lot of basic science that we do, which we can talk about and we can write papers about. What we end up doing is carrying a lot of that understanding into our actual classified work, which obviously we do not, talk about or
Sure.
publish.
Again, coming back to the theme of theoretical chemistry or quantum chemistry or whether the appropriate term is. We talked a little bit about helium at the beginning and some of these unique nanostructures that you were studying, nanocrystalline structures, obviously applications, as you were mentioning, everything from photovoltaics, quantum computing, and so forth. What else? When you're not thinking about fusion experiments or the nuclear stockpile, but really, coming back to your core, which is this theoretical chemistry base. What are some of the other things that you envision specifically? And I don't know if they're capable of being studied within the NIF or with the tools that you have at the NIF, but when it comes to sort of the next stage of where we're going with chemistry. And I bring that up because another person actually from local here outside of Philadelphia was a Dr. Michelle Frankel, and she's a quantum chemist, and she was talking about stuff about something called Mobiusines, these interesting aromatic molecules that look like Mobius ladders, and all sorts of other things that went over my head. But where are we going sort of with the frontiers of theoretical and quantum chemistry?
Yeah, so that's a great question, and I will readily admit that because I've spent the last 15 years working in high energy density science, I'm probably not the best person to answer it.
Okay.
Now, I can answer it in the context of the stuff that we do with the lasers, which
Please.
I think if I go back 10 or 15 years, there were a lot of sort of extreme chemistry types of things that we were looking at theoretically, very high pressure phases where you can actually force helium to form molecules, for example, or to form a solid lattice with other elements. And things like superionic ices, which are very high density but also high temperature types of solid materials where essentially the hydrogen atoms can become very mobile and sort of move through the solid lattice of oxygen, for example. So some of the exciting work that we're doing in the realm of materials science and chemistry at the NIF really aims at understanding those sorts of problems like superionic ices. There's been a number of experiments done on that, looking at issues like shock refreeze in carbon, which is if you shock a material, generally, you want to shock it hard enough that it's behaving like a fluid for our ICF experiments. And there's a possibility because of the complex phase diagram of carbon that it sort of bounces back and forth between solid and liquid as it's being shocked, depending on how hard you hit it. So we've actually done some experiments at Omega and at NIF to look at carbon refreeze that are very interesting. And those also tie in with more like astrophysics and there's a kind of new field called cosmochemistry, for example, where we're sort of interested in like how molecules formed in the origins of the universe, and so these kinds of laser facilities really give us insight into those things. I think looking at chemistry with somewhat of an outsider's perspective at this stage, I would say Some of the things that excite me are the application of AI and modeling tools to theoretical chemistry. I remember back when I was a grad student, there were these sort of games you could play online where you try to like help them build a protein. It was some research group somewhere that was doing research on protein folding. And it's such a complex problem, and the search algorithms are so hard to, have them run efficiently, that essentially they had farmed this out as a crowdsourced problem, back in 2003 when, nobody was crowdsourcing. And you could go in and it was a game, literally, use your chemistry knowledge to try to help us like fold this protein. Well, nowadays, you can take all of that, all the games that people played, all the actual, physical simulations that someone could have done, and sort of put it into an AI machine and see what the AI thinks is practical. And I've seen, some research that's been done in chemistry where they're looking at like much higher order correlations between different variables and how those come together to really inform our understanding. I think biology is one of the frontiers, and biochemistry is one of the frontiers where there's a lot to be done. It's very exciting. I mean, I think the pandemic shows us, in some sense, how important, biology, bioengineering, biosecurity really is for our country. And, actually taking the kinds of theoretical approaches that I applied to very small systems and being able to apply those to much, much bigger things and really understand fundamentally, how the human body works, how viruses work, I think is incredibly exciting. Neuroscience is exciting as well. I mean, the human brain is so complex, and there's there seems to be a lot of analogies between quantum information and the way that our minds actually work. And, fundamentally, it's probably all chemical processes that are underlying that, and starting to understand better how those things happen is really exciting to me.
Yeah, and I appreciate you brought that up because we have done a couple of quantum biology shows, and there's another area that just it's embryonic, but as you were just pointing out, the connection between chemistry, biology, and sort of the quantum domain. There's just so much more we're going to be learning. So that's it. I thank you for being the chemist that brings up biology. So that's awesome. What if you would, could you say a few words about not just your leadership? I know that you have, in addition to your role, you also served as the president of what's called the Lawrence Livermore Women's Association. And when you joined, not a lot of women around doing this type of work, but at the same time, and I guess this sort of resonates with Annie's story, doing some really advanced PhD stuff, and boom, Livermore wants you, and you come. Any interesting programs that you're involved in, and sort of pulling in that next generation of the Heather Whitleys and the Annie Critchers that are out there to potentiate this amazing sort of future that you're working on?
Sure. So that is a great question. And, so I was the president of the Women's Association 2016, 2017 timeframe. So it's been a minute, but back in that timeframe and before that, we had set up the Women in Science and Engineering group here at the lab. That was actually what brought me into the Women's Association. I had just started a networking lunch for women at the lab back in, I think it was like 2012 or 2013 that I started that. And when the Women's Association found out about it, actually because the then president was on the board for the ballet that I danced in at the time, she heard about what I was doing, and she said, well, why don't you come back and reconstitute this Women in Science and Engineering committee that was part of the Women's Association and sort of has been inactive for the last few years. So I did that. And we did spend a lot of time sort of understanding, like, where do women sort of drop out? And it actually turns out that it's at every phase of the career process, going all the way back to like 5th grade. So around 5th grade, 6th grade, middle school, that is a big turning point for many girls who are interested in STEM fields. And so I actually have a lot of passion about reaching out to like the elementary school, right? Middle school. So Lawrence Livermore we have our Science on Saturdays series, which is sort of a broad outreach that we do. We run a Saturday workshop called Expanding Your Horizons every year, where we bring in, it's middle school and high school age girls, and they have like an entire immersion, a day-long immersion into different science projects. At the lab, I've participated in that a number of times. And then we also just started last year a summer camp for girls who are interested in science. I believe it's only high school ages, and it's called SAGE, S-A-G-E, and actually the applications are open right now, I think through April 14th. So that's open to high school students in Northern California. I'll mention as well that uh, Los Alamos runs something similar for high school students in northern New Mexico. It's like a week-long summer camp for girls. And then other things that I've done, I've mentored young ladies from Las Positas College here in town. And they've gone on to do great things actually in the health field. They didn't necessarily come to Livermore, but we have our summer internship programs too, which I was really excited to hear Annie's story. I didn't realize that she had come here in 2004 as a summer student in health physics. That was news to me. So we bring in a lot of folks, but you're right. In my career starting out, I would say it's sort of gone from, being the only woman in the room to being one of many during my career, which is exciting. But what I've observed is that there's like nucleation points, if you understand what that means. Like when a solid forms, usually it's like something starts to form a little solid and then the solid builds out around it. So what I've seen is that it seems like when we have like one or two women who are leaders here at the lab, we start to nucleate more women around them. And it's not like it's intentional. It's not like we're trying to do it. It just seems to happen. So I remember, coming here and, like I say, being like the only woman. And then ultimately when we were doing those equation of state experiments with Annie, and Amy Yanay was the lead for many of those experiments on the experimental side, there were times where like the women actually were outnumbering the men in the room. And that was where I really started to notice, like, hey, it really looks like our representation is getting better. Now, that being said, I don't want to paint an overly rosy picture, because I do know that in plasma physics, I think women are still only like 12% of PhDs. So that's a pretty abysmal number. And the way that we improve that is to continue to be more inclusive and to people of all genders. It's not just about bringing women into the field. It's really about creating an environment where everyone is welcome and, really appreciated for who they are, and not, sort of expected to fit a certain mold.
Excellent. Really excellent. And you mentioned it too. I have to ask, and I was reading not just about your early career as a ballerina, but you performed many of the Nutcracker as well as other ballets. Are you getting much time in to perform or practice or teach? And I know you're also a teacher of ballet students, but what's going on that front?
Yeah, so I'm really excited that, yes, I've been able to stay involved in the ballet, and I'm now, going on 43 years old. So the physicality of dancing on point and things like that, unless you dance professionally, those things fall off kind of, around this time. So I don't dance as intensely as I once did, say 6 or 7 years ago. I do still get to participate in the Nutcracker, and I actually choreograph and teach the rehearsals for some of the youngest dancers in the performance in the Nutcracker, and that's really fun for me. I actually don't have any kids, and I really enjoy spending my Saturdays during the fall time. Basically, it runs from October to December almost every Saturday. And then we actually do 10 shows of the Nutcracker every year. with the studio that I dance with. And so, I've been doing the Nutcracker with Valley Dance Theater here since 2012, or no, 2010.
Okay.
I've probably danced in like upwards of 100 shows, I would guess. And I've had, my students have definitely danced in more than 100 shows if I integrate up over all that time. So I'm actually really proud of that, although I would in no way, brand myself as a professional dancer or a professional dance teacher even. It's just something that's really fun. And we actually do a couple of shows for free for schools here in Livermore. And it's just a community outreach thing as well, which is awesome. And it's introduced me to a whole other world. And I will say that dancing actually has influenced my communication style and my presentation style quite a bit. I was thinking about this, and if you ever watch Balanchine's version of Snow from the Nutcracker, it
Okay.
really builds up to this sort of, apex or peak in the music around 3 minutes and 30 seconds in. And that continues on for a couple of minutes and then it goes back down. And I think, if you watch that performance, there's all of this little stuff going on that kind of brings the audience in and helps them to follow up to that point where all the dancers are on stage and there's so much stuff happening. That's kind of how I format presentations. I try to have a lot of little pieces and then there's like a peak. And then at the end, it calms back down and it hopefully brings everybody back in, to the
Mm-hmm.
nucleus of the story back, when the main character and her Nutcracker prince come across the stage, it sort of brings the audience back in. So even if you got lost in that flurry of activity, you come back in. So yeah, it's interesting how it's interesting the intersection of art and science. Actually, I always
Yeah.
thought I was very not creative growing up, but I think as an adult, I've learned to appreciate the aspects in which I am creative, which isn't drawing or painting or any of those things.
Well, it's yeah, I mean the connection, as you were just saying, between art and science is quite evident here. And in all these areas. I mean, there's it's impossible not to see, especially when we're talking about some of the more esoteric parts of physics and chemistry that you've elaborated on today. So yeah, no, really amazing little journey here, Heather. One last thing while we have you, I noticed that you're, in addition to everything going on at Lawrence Livermore, you are also quite active in a lot of the public facing educational things happening. You just National Defense Industrial Association, you were involved in a talk just a couple of days ago on nuclear fusion 101. I think some the American Physical Society a couple of months ago talking about plasma physics. What's coming up for 2023 in terms of conferences, talks you're going to be giving, any other public facing initiatives where we can watch you, listen to you, potentially meet you? Please take the floor on that one.
So that's a great question. I think right now I don't have another engagement scheduled at this point, but I'm more than happy to come out and give conferences. I will say New Mexico State has reached out to me, and so I do anticipate that at some point I'll probably be giving a seminar for the Alumni Association out here in California and hopefully making it back to campus at some point to New Mexico State University. Otherwise, I don't think I have any additional public engagements coming up. This was sort of the last one that was on the calendar for the time being.
Well, we will keep our eye out on you anyway, just because I mean you are working in such again cutting edge, bleeding edge domain of not just chemistry, the connection to biology, obviously the future of our energy system, and just the future of exploration on such an amazing time in our scientific history. So I mean, I really wish you the best with everything you're doing as you continue along this path of experimental sciences. Again, for everybody that's going to be listening to this particular episode of our show across the various podcast networks or watching on the YouTube channel, again, you've been listening to Dr. Heather Whitley, Associate Program Director, High Energy Density Sciences, Weapons and Complex Integration Director, Lawrence Livermore National Laboratory. Heather, I want to thank you again for taking the time out of your schedule to come talk and educate us for a little while on these themes. Obviously, thank you for what you do to sort of usher in this new generation of scientific potential. And as we say on our show, thanks for helping to create a better tomorrow for all of us via what you do. Really, really great story.
Sure. Thank you.